Good afternoon to our audience and to our speakers, and a very warm welcome to this fifth webinar in the Brain Matters series, which is hosted by the Human Brain Project. Now, in the next 60 minutes, we are going to give you a fabulous introduction to the EBRAINS virtual big brain. My name is Katrina Sickle. I'm a broadcaster and a moderator, and I really do have the privilege of navigating you and 4 expert speakers through this webinar, in which we slightly shift the focus from scientific results to scientific activity. And we're going to have a look at what's currently underway in the final phase of the Human Brain Project. Now, what about the virtual big brain? This is where it gets fabulously interesting, because teams in Germany and in France are working very, very hard to put together a massively scaled up version of the virtual brain. And this is a tool. It simulates the whole brain using mean field models. Now, if you've been a regular in this series, you'll know that we are really aiming to speak to everybody, from the hardcore specialists at one end to the very interested non-specialists like my good self. But for all of you, no matter your expertise, we really do invite you to make your voices heard in this webinar. And all you need to do is post a really short question into the chat channel on your social media platform. And I'll take some of those questions, I'll weave them in throughout, and some I'll leave to our Q&A section right at the end of the event. Of course, if you want to make your voice heard at any time, you can do so on Twitter. It's #BrainMatters and also @HumanBrainProj. Very, very important, ladies and gentlemen, when you ask questions, please keep them as short as possible and say to whom they are addressed. That's really helpful. Now, I said I'm joined by 4 eloquent speakers. I'm going to get the first of those speakers on screen with me, and he is Victor Gerser. So if I can ask you to come and share the virtual space. Victor, hello. It's really, really lovely to see you. For those who don't know you, you're director of the INSERM, Institut de Neurosciences des Systèmes at Aix-Marseille University. I was going to say university, but I said université. And of course, you've been here in the first, you were kicked off this series last autumn with me. So hello, how are you doing? Do you have sunshine?
Of course, we're in the south of France. How are you doing up there?
How am I doing in Brussels? I'm looking out my window of my office in my house. Yes, we also have sunshine. Maybe not quite as gorgeous as yours, but we do have sunshine. Now, you are the scientific lead of the brain simulation platform, the Virtual Brain, and you are lead investigator in the Human Brain Project. So it's absolutely delightful to have you here, because you are going to do that really important job of framing the content for this particular webinar, where we're putting all the focus on the virtual big brain. So tell us, I'm going to let you present, and then I'm going to put you under the spotlight and grill you with a few questions.
Thank you.
Let me give you a moment. There we go. I can see your presentation. That's already a good sign.
Yes.
So yes, I give you time.
First of all, it's a pleasure to be back here again, and nice to see you again. The virtual big brain is something that we are currently developing in the Human Brain Project and in EBRAINS. And what we want to do is we want to build digital copies of individual brains. These digital copies, they serve as independent simulation platforms that guide the development of future neurotechnology for both diagnostic and curative purposes that shall then help in the clinical decision making. And the question is, how do we do this? What we already have in place is a technology which is called the virtual brain. Yeah, and for the virtual brain, it's a hybrid approach where we are linking high-level mathematics and computation together with actual data from the subjects, human subjects or patients. And what you see here is an MRI scanner, which allows us to extract structural anatomical information of an individual, and then we put it together with our mathematics that allows us to build these computational models of a brain. So what we extract in particular is, on the one hand side, the cortical and subcortical surfaces, and with the same scanner also the connectivity that you see represented here. This we refer to as the brain connectome. And the geometry is up here. This is topographical information that allows us actually to parcellate the surface, the cortical and subcortical surface, into network nodes, individual brain regions, which allows us then to build a network. And this is how we do that. Yeah. So we take the individual network nodes, the regions, cross-reference it with the patient-specific, the individual connectome, and put it in the same reference space that allows us then in EBRAINS to span it in the physical head, so a physical head copy, of course, of the patient, and then equip it with mathematics on the individual network nodes that you see here that allow us then to simulate the network activity and project it up to EEG or MEG, so all the windows that we take to obtain information into the human brain non-invasively and extract that from the patient's brain activity. So this is a link. This is very special because on the one hand side, we look individual information, we look link mathematics together with actually our entry point, the brain imaging signals to the human. Yeah, this is a summary statistics what we have. Usually in the virtual brain, we work with 100 to 200 network nodes. These are the regions, and there are about 10 to 20 square centimeters. So they're quite big actually, like the parcels I showed you earlier. And these are the fiber lengths that we have there on the centimeter scale. So this is a range we are working with, and this technology finds already applications. For instance, we are running in Europe the first clinical trial in epilepsy, in drug-resistant epilepsy, guiding epileptic surgery decisions with 400 prospective patients. So this technology is useful. And here you see an example of the type of invasive measurements we use in epilepsy. Yeah. So, but how can we make this better? And for this, one key question that poses itself is what matters the most in this context? What is really important? And we can actually address it. Here we've done that in a mouse model. We can actually address it systematically. Yeah. So what matters in order to improve the predictive power that is plotted here? And we can either we can scan here for in the context of a mouse, the same mouse again, where the mouse itself serves as its own model. We call this scan-rescan variability, and that's the best we can do, and go all the way to the other end of the spectrum where we deal with very generic brain models, brain templates that resemble a mouse brain. Yeah, but in between we have a whole range of other solutions. For instance, we can you construct mouse brains here from high-resolution data of hundreds of mice, where we have gold standard data where we reconstruct with tracer studies the individual tracts and get a very detailed model. Also, so we can build a brain atlas with connectivity, multi-scale information, and put lots of detail in there. Or we can actually scan the same mouse as we do it in the human and perform the reconstruction of the connectivity and use the same technology as in the human. The advantage is here we have an individual brain. Here, of course, we lose all individuality. But if you look at this in terms of predictive power, the high resolution does very well. The scan-rescan variability, we are almost 60%. Here we're not far, almost 50%. And this is for the individual brain. It is also still better doing than the generic brain template. So what we learned from this is actually that individualization is good, high resolution is good. If we can get these two things somehow together, we are approaching actually the real brain. And this is what we do in the virtual big brain. We are putting these things together. Yeah. And here you see a representation thereof. And here you see the statistics. We are talking about 200 to actually 260,000 network nodes. So that's a factor 1,000 more. We are on a size of the regions on the millimeter scale, and or for the fiber lengths on the 100 micron scale. So we get very detailed models.
Okay.
And what we do in the virtual big brain now in the EBRAINS is the following. You see two streams here. This is a classic route where we go from individual brain data, functional, structural, build the virtual brain, and then make estimations and build copies of the patient's brain, the virtual brain. Here, we use a high-resolution information that for the human, we don't have it. We can get it from high-resolution scans, but we can also get it from post-mortem data and many decades of studies, put them into a multi-scale representation of individual brain regions. So we put everything together, yeah, but then we don't have it personalized. For the personalization, we use methods from machine learning and artificial intelligence to fit it best to an individual brain. And this is our construct that builds our virtual big brain to improve the predictive power in the applications. Yeah, and this is what we need EBRAINS for. Yeah, and
I'm going to give you you're there. I was going to say I'm going to give you, because I'm going to come back to you. Do you mind if I'm not going to keep you for so much longer, because I'd like to give a chance for everyone to present, and then I will come back to you. But as far as I understand it, one of the biggest challenges in neuroscience is the issues related to the brain function variability. And this is where this is particularly important from what you are presenting here, because it allows you to zoom in and zoom out. It allows you a lot more precision. So in a nutshell, before I move on, why is it so very important?
Yeah. In applications, in a nutshell, in clinical applications, you want to help this particular patient, not the entire patient group, but this particular patient. And there's a large inter-subject variability. This is where the personalization comes in. We have a large anatomical structural variability, which affects actually the brain activations and also in the simulations. This is why it's important. Yeah.
Okay, and we're going to talk more, and I want to just reassure the audience, Victor, if I'm correct, that later perhaps we can talk more about, how you can learn to use it, where, when, much more of the accessibility of the virtual big brain. We're just going to focus now on the kind of the story. You've delightfully set the scene, the story that's going to be told through our other three experts. So if I can ask those three expert speakers to join us, they are your colleagues, of course, and that's the great, I don't know, what should we say, the beauty of the Human Brain Project is it's gathering together all these people with so many different specialisms, and that's pretty unique. So do you want to just say a little heads up on each of them, how you see them fitting into the story, Victor, and then I will take over. Welcome, Marmaduke, Timo, Sandra, first of all. Nice to see you. Hello.
Hello.
Actually, yeah, I'm very grateful to have these three people here. In the workflow, they play very important roles in the workflow of the virtual big brain that I showed you. Marmaduke is a computational neuroscientist in Marseille at the System Neuroscience Institute in Marseille, and he's been with a virtual brain for a long time. He's a computer science expert. He's responsible for the curation of the virtual brain. So he's an expert in this domain and has overseen this platform for a long time.
Okay, and I'll just dob in there, and I will say, just for streamlining this for the audience, so Marmaduke is going to talk about how we build up a virtual big brain. That's part of the story. Okay, I interrupted you. Talk about Timo. Hello, Timo.
Perfect. And the other part of the story that Timo Dickscheid will build up is actually linked to the Human Brain Atlas. Yeah, because we need a space in which we can navigate and organize all this information. And he is in Jülich at the Forschungszentrum in Jülich in Germany. He's a computer scientist and oversees a large part of the building of this informatics elements in EBRAINS and in the Human Brain Project. Yep. And then finally, we need large computational resources in order to use the virtual big brain. And this is where Sandra comes in. Sandra Diaz, computer engineer, also in Jülich at the Forschungszentrum in Germany. And she's making the interface. She's responsible for what we call the high performance computing back end. Yeah, so she's between the supercomputers and making sure that the virtual big brain is actually optimized for running on the supercomputers, and we will learn more about her work later on.
Thank you. And let me just suffice to say, ladies and gentlemen, that I would be both excited and terrified to sit next to any of you at a dinner party. There we go. So you've done a splendid job, Victor. I can ask Victor and Timo and Sandra to very briefly take a back seat. I can ask Marmaduke to stay with me. Marmaduke, who is, as we heard, a neuroinformatics engineer at Aix-Marseille University. Just before I give you the floor, Marmaduke, can I remind our lovely audience that you can ask a question, super short one, at any point, and then I'll try and weave it in after each presentation, or I might save it to the end when we have a kind of a quick fire round with all four experts together. So you work on the virtual big brain, Marmaduke, you work on its applications. Can you talk to us about how you build it?
Yeah, I'd be happy to. So I'm going to go briefly through I'm going to go through the virtual big brain, but to start out, I want to say that the virtual brain is actually a confluence of multiple sources of data. As Victor has already shown you, we're taking the structural imaging data, the connectivity between the regions, the patient's or subject's specific functional data, these are time series, and injecting this with high resolution postmortem data. And this is what becomes the virtual big brain, a much higher scale than what we can do with the data frequently available for just living subjects. But what we're going to do first is go through the virtual brain itself. The virtual brain is a software that has been under development for over a decade within different groups. And it's actually available on EBRAINS already. You have some addresses here where you can go, click on this link here. And if you have an EBRAINS account, you can already log in and start using the simulator. So the TVB, or the virtual brain, is software already usable on the EBRAINS platform. So what we want to do is to scale it up. Now, these are screenshots out of the TVB software. I wanted to keep it concrete. These are things that we get out of the TVB interface. When we have the cortical surface here, it's divided into parcels, which are in different colors. Each of these are represented on the small scale as a single node. These nodes are equipped with mathematical models of the activity in those nodes. But those nodes don't exist in isolation. And the virtual brain connects these different nodes with a connectivity matrix. If the nodes or the regions in the brain are neighborhoods, then the connectivity between them are like the roads or the subways that allow for information flow between the regions of the brain. And there are two kinds of connectivity modeled within the virtual brain. We have on the left an image of the white matter fibers that traverse the whole brain. And on the right-hand side, we can see an example of the local connectivity between, these would be the lateral fibers that travel along the surface of the cortex. Now, to give you a better idea about what's happening with the virtual big brain, is that we're scaling up the resolution of the model. So on the left, you might see you have an image which represents the state-of-the-art perhaps until recently. And now on the right, we have an image which represents the resolution of the models that we're now able to simulate with the virtual big brain. But to make the link to a subject, to personalize these models, to make them specific for a given subject or patient, we link the virtual brains to the functional data. These are data which are acquired with EEG, with fMRI, typical neuroimaging modalities at hospitals and research centers. And the virtual brain can be used to tune the model to the individual's data to have a personalized brain model. So together with in the virtual big brain, we are putting these elements together to achieve a millimeter resolution in cortex, to inject regional variability data that we get from post-mortem data sets. And this simulation is then performed in real time with some of the new algorithms that we have put in place. And lastly, it can be personalized and made subject specific. Just to give you an idea of what this looks like when we simulate, I'm going to run a video here. This is a video of a seizure propagation in a personalized brain model. And so we can see the seizure has started at the temporal lobe pole, and it is propagating now along the temporal pole towards the back of the brain. And this level of detail at this speed was simply not possible even last year. So this is a rather innovative aspect of the virtual big brain.
I'm not interrupting you because you hadn't. Hang on, you're dealing with your. Are you trying to move on or to switch off your video?
And well, I didn't want to run it again. I just wanted to go to the next slide. Yes, thank you. So I'm done now. I'd be happy to take any questions. Yes.
Thank you. Well, the questions are going to be from me. Absolutely, and really, really useful to see that animation at the end. And what I caught there is you were talking about millimeter resolution in the cortex.
Yes.
So we're looking at the scale up in the cortical structures.
Yes.
So I think the obvious question for you would be, if we're talking subcortex, what sort of the plans there in terms of the scale up?
This is a question. Thank you. This is a good question we've been asking ourselves, because the subcortical structures play as important, if not more important, role in the brain than the cortex itself. The primary issue is that so far we haven't got good high-resolution models for the different subcortical structures. However, other groups do, and we are looking forward to interfacing with other groups for a high-resolution cerebellum model that's also being developed within the Human Brain Project. So that's on the horizon.
Okay, fantastic. Well, hold that thought a second, because I'm going to ask Victor, who should be lurking in the wings, to come back. He's there. Hello. It's all a bit like a game show, isn't it? When we all appear in boxes like this and wave. It's sort of game show with all of this high intellectual output that you are all exuding. So Victor, anything that you wanted to ask or comment on there, or perhaps add for the benefit of our audience?
Maybe very briefly, Mohammed, you could say a word or on the challenges when making the transition from virtual brain to the virtual big brain, because it's not just the computer power that is being affected there, but there are some other aspects that are important: neural fields, personalization, etc. Maybe you can say a few words on this.
Sure. One of the major challenges in building the virtual big brain is to assemble the data. The data which feed into the virtual big brain, these come from very different sources, and they require a co-registration. They require alignment so that the simulation makes sense. If the input data are not aligned and not verified, they simply do not. The simulation will not make sense. There are computational challenges, of course. There are changes in algorithms that we have done in order to perform this scaling up. But yeah, the main challenge, I would say, is in terms of the data.
Okay, I'm going to hop in there because I can see there is some activity and some questions. Before we take the first of those questions, I'm just going to come back, because all of this is about applications. And when Victor was doing his presentation at the beginning, he talked about where it's being used in epilepsy, I think also looking at Parkinson's, but we can talk more about that. But what are the potential applications for brain-computer interfacing?
So in the I don't know that much about brain-computer interfacing myself, but some of the applications we could foresee, for instance, would be to aid in the reconstruction. So in a BCI setup, we have sensors in the brain which are trying to interpret what's happening in the brain for the purpose of interfacing with the computer. And some of the new mathematics here would allow for these sensors have a better reconstruction of the activity of the cortical activity, and this could assist in improving the BCI interfaces. The other aspect of being able to do this simulation real time means that the model can simply run on the computer next to the individual and tune itself along with the person as it's interacting with them, and that could open up some interesting improvements in BCI.
Okay, Victor, unless you have, and you can, because I'm going to ask for a couple of questions, just for a couple of quick, let me not terrify you, Marmaduke, for a couple of concise answers. Victor, anything to say before I do that? Anything?
No, let the people ask. Yeah?
Let the people, oh, I love that. You sound like Marie Antoinette. Let the people ask. Okay, I think we did have a question from Marmaduke. There we go, and you can see it yourself, Marmaduke. Can we have some of these zoom in, zoom out information in a simplified map? So these various uses.
Yeah, the data and the computational technique itself are things that will become available on eBRAINS. Absolutely, they're currently under development. So and by this I mean I was working on. I finalized a piece of code last week to do some of these simulations. So we are preparing this to put it onto eBRAINS, and then it will absolutely become available for EEG and fMRI purposes. Yes.
Perfect. I don't know if there's one more for Marmaduke because I know questions come in that's probably more relevant for Timo, and Timo is going to be presenting next. So I will just see if anything specific has come in for you, Marmaduke. I know there's a bit of activity. There we go. We'll take one more before I close this little part. And don't forget, ladies and gentlemen, I'll be posing your questions again towards the end of the webinar. So there we go.
So I apologize to Timo, but I will punt this question over to Timo because the relation with the postmortem data I can't make any statements about. I've really been working on the code and the computational techniques.
Maybe can I add something very quickly to this? The postmortem data are of very high resolution, and from the animal experiments and the animal studies, we have seen that the predictive power of this high resolution information is actually increasing a lot when we add this in. So, but there we are losing this aspect of individuality, yeah? So, which is completely orthogonal to each other, which means we need to find good workflows that allow us to take advantage of both pieces of information.
Thank you very, very much. So I'm going to let you two gentlemen take a back seat because Timo obviously not only has to present, but already answer about 5,000 questions. And Timo, you also have apparently roadworks going on behind you. We were saying that have you got roadworks? It is you.
I think they're done, Katrina.
Jeez, that was the quickest. Can I just tell you, roadworks in Belgium don't go at that speed, which as far as I can ascertain from reading the private chat was 45 seconds. So you have a lot of work to do. You are working group leader in the Institute of Neuroscience and Medicine at the Forschungszentrum in Jülich, and there you are leading a scientific research group that focuses on big data analytics for biomedical image processing. So you're going to tell us the next part in the story, the concept of the eBRAINS multi-level human brain atlas, how it's embedded in the eBRAINS infrastructure, how it supports the brain simulation with comprehensive information on human brain organization. Let me just remind the audience, questions can come in and I will decide when and how I can pop them in because Timo's already got quite a few to answer. There you go, Timo, the floor is yours. Thank you.
Thanks, Katrina. It's a pleasure to be here. And talk about the brain atlases in the Human Brain Project in particular, how they fit in with this project of the virtual big brain. So first of all, we are building a range of brain atlases from different species in eBRAINS, and there is this webpage on the eBRAINS portal already available to everyone, where you find the link here on my slides. And there are atlases of the mouse and the rat brain, and of course of the human brain. This is what I'm talking about today. And there is an atlas of the monkey also coming up. So stay tuned and find everything that we are talking about on the web portal. that is shown here. So that being said, let's dive a bit into what these brain atlases contribute to the project we are talking here today, the virtual big brain. And this is, of course, first of all, as already mentioned by Marmaduke and by Victor, first of all, the definition of brain regions. And the Human Brain Atlas in EBRAINS has this specific ambition to cover brain regions on different levels and scales. In particular, it provides probabilistic maps that have been delineated in different individuals to represent some of the variability that we see in the human brain. And at the same time, we have links across the scales and can provide maps according to the same criteria at full resolution, at the micrometer resolution, in what we call the big brain, which is a template model of a human brain at microscopic resolution. So we are covering here multiple aspects of brain regions at different scales. But second, and that has also been already motivated by the previous speakers, the Atlas provides features of different brain regions, and these are mostly multimodal data sets that have been measured in those brain regions. You can see here on my slides a few examples only. In particular, what Marmaduke was saying, there are features that have been measured at the microscopic scale from postmortem studies, microscopy. For example, you see here on the left distributions of nerve fibers. You see here in the middle densities and distributions of neural cells. And on the right is an example what it would look like to see distributions in the cortex of certain neurotransmitter receptors. On the bottom is another example which shows functional activity, which has been measured in vivo. And these are only a few examples. So we have such features for different brain regions, and this can be used in the models that we have just been seeing. And then third, what we provide is, of course, measurements of the connectivity between those brain regions, which typically comes from cohorts of multiple subjects and is measured according to different principles, structural imaging, functional imaging, and so on. And often we refer to these connections as connectomes. So now, all of this rich information from the brain regions to the different data sets, data features, and connectivity, these are in fact all data sets that we are hosting in EBRAINS by the EBRAINS data services. So all of these ingredients of the atlases can actually be found in what we call the EBRAINS knowledge graph as a curated data set with rich information, at least most of them. And what the Atlas services that we are developing are doing is they organize this data in terms of brain regions. They do a multi-level integration of all these informations by brain regions, and they provide software interfaces to actually work with it in a very easy fashion in anatomical space. And one way to do that is through interaction with a web application. As you can see here, there is an interactive web browser, and here you can do what I have just described. You can select different brain regions. You can see the probabilistic maps. Here you see some intracranial recordings that have been measured in the selected brain regions here in the back of the brain. You can also see here how we find measurements of neurotransmitter receptors in that particular region and more. And as you can see on the left, you can always switch to the higher resolution, to the microscopic resolution, where you find corresponding region delineations and access to the same type of data. Yeah, let me move on to the next slide here instead of going through that whole movie. But of course, this web interface, this interactive viewer, is not what the big brain would be using. Sorry, the virtual brain would be using. This is a software, and of course, this software doesn't fire up a web browser to click around in an interactive viewer. So of course, there are software interfaces to these Atlas services that can be used in a programmatic fashion, in the way that the virtual brain would be doing it. And there is, for example, and in particular for our webinar here today, there is a Python client that allows to do these same interactions that we have just seen interactively in a web browser in a programmatic fashion. So here a programmer can actually connect to the Atlas services, select brain regions, find these features, browse the connectivity information, and do that in a reproducible way just through software. And this allows us to make this connection between the virtual brain and this multi-level brain atlas. Yeah. And with this, I'm at the end of the talk, and happy to answer some of those questions.
Thank you. I was trying to read your cues there because I'm not with you. So you sort of go, yeah. And I'm thinking, is he going to go on and say so, or is he finished? Is it a yeah that finishes it, or is it a yeah that takes you into another thought process? So I was just hanging on there. It's absolutely astounding. I have a couple of questions. I'll invite Victor back. Well, Victor, come whenever you like, because first, just for some quick answers, just what excites you about this? That's it. And again, just to echo Victor's question that we had to Marmaduke, what are the challenges that are inherent? Excitement, challenges.
You're asking me, not Victor, yeah. So to me, it is really fascinating. Now, I'm working for quite a few years now in the neuroscience, although I come from just from the computer science field. We are working for quite a few years on these brain atlases, and this is really measuring the brain, yeah, just like meteorologists measure the Earth. But now in this project here, it is really interesting to see how these measurements actually have an effect on the other side in doing brain simulation. How you see how this knowledge actually makes a difference in understanding this domain of the brain. This is really fascinating to me, and it is also always very inspiring and surprising at the same time. In which way people who do brain simulation want to use the data and the information we have. This is different from what we have been used to in the past when interacting with more experimental scientists and so on. So this is really fascinating.
And just let me link my question about challenges to, and then Victor, I promise I'll give you the floor to data, because this is all about data. You've just talked about it there. You said that the data is organized into brain regions, and you were, showing how that you can actually work with that there at the end of your presentation. But this is very large data volumes. It's very high image resolution. So how does the creation of the human brain maps depend upon the manual input? I mean, how is that happening?
That's a great question, and this is something that we are working on a lot. So classically, this is a rather manual process that requires a lot of expert input, mapping those brain regions in tissue sections of the brain. But nowadays, that we try to go to high throughput imaging, and through this whole brain 3D models at high resolutions, this cannot be done only by an expert. So we are developing methods from artificial intelligence that can learn from the experts, from all these decades of knowledge, to help us doing this cartography, if you like, in much larger amounts nowadays of imaging data to produce these high resolution maps at full detail. So here we rely on artificial intelligence.
Let me just give a heads up to you and to our audience and to Victor. So Victor, I'd like you to just chip in there. Then we could take one question, because I know that we'd had a few from the audience, perhaps one or two, if they're not too complicated for you to respond, Timo, quite concisely, and then we can leave the rest for our end, because I'd like to give Sandra a chance to put the next bit of the puzzle into place. But Victor, over to you. What would you like to add or ask?
I'd like to add something, but actually I see we are being bombarded by questions, which is great. Yeah. One comment I would like to make, what we've been doing with the virtual brain and its applications, we are exploiting the network character and the network features. But by going into this multi-scale detail that is being provided by the Human Brain Atlas, what is exciting in there is actually we can go across scales and then connect to the underlying physiological mechanisms, because we have multi-scale models available for each brain region. And that opens up completely new dimensions for asking questions about causality.
Yeah. I think you called it, I think when we were chatting before this, you said it is unique worldwide. I think that was your Or did I grasp? Yeah.
No,
yeah.
you got it right, because there are big projects like the BRAIN Initiative in the US, Japan, Australia. But in Europe, with EBRAINS and the Human Brain Project, we are the only ones worldwide that are actually putting the emphasis on the modeling.
Okay, I saw a question for Timo, and you're absolutely right. There is so much activity. So let's just see this one, possibly another, and then I will release you two gentlemen and invite Sandra. So there you go, Timo.
Yeah, will the postmortem data be available? Of course, this is something that that we are after. So already now you find a lot of postmortem data in the Human Brain Project's knowledge graph and storage systems indexed. And the features that I've shown for the Atlas, here we have some different cases. We often try to provide samples from the postmortem data, so it's quickly and easily available. But we are working on ways, and I call this always the big data access to the Atlas, to really go into the large data sets. And really, the postmortem data for human brains, it's really huge. We are talking here about hundreds of terabytes of data. And it is really a technical issue how you provide access to it. How could somebody browse this huge amount of data? But we are working on that, and there will more and more of this full postmortem data will also become available.
Okay, thank you. Can we just get one more? There you go. Let me give you a chance to read that. I don't need to read it out since you can see it.
Yeah, so tissue clearing data is something that researchers and labs in the Human Brain Project are working on, and tissue clearing data is coming into the eBRAINS knowledge graph. There is already some of that available. Most often these are regional data, so this is very often covers certain regions of the brain, and our approach is to link those with the big brain, so to really bring them into the appropriate place of the big brain, link them from there so you can find them. Yeah, I have to forward it to Victor regarding the last part of the question, whether that would also go into the virtual big brain and use there. So this is something that Victor can answer better.
Very rapidly. At the moment, we cannot address that. It's a matter of the complexity of the brain region models that we have. And we can use certain parameters that can be translated, but not a complete set. This will be ongoing work that will accompany us for decades.
Thank you, gentlemen. Thank you. More questions coming in. There's a whole vibe and a buzz, and that's brilliant because that's what these webinars are all about. So kindly just put your feet up backstage. I'm going to invite to join me Sandra Diaz. So she has been incredibly patient. There we go. Now, let me just remind, just before I ask you, let me just remind our audience that you're a graduate researcher at Forschungszentrum Jülich. You study the plasticity of neural networks using simulations on high-performance computing infrastructures. So I'm going to ask you to take us on this next bit of the virtual big brain journey and talk about how high-performance and interactive computing support the virtual big brain on eBRAINS. Thank you.
Yes, thank you so much for having me here, Katrina. It's a pleasure to be here. And yes, as Victor said at the beginning, I am in charge of developing this high-performance computing backend for this very advanced use case in neuroscience, which, as you already heard, each piece of this workflow requires high amounts of computing power, and also large amounts of data storage and accessibility to data. So we want to be able to interact with large amounts of very specific, detailed information, and we want to be able to integrate that into our models. So, of course, if we would think about doing this on a normal workstation at home, this would probably take months or years, if even possible. On the other hand, if you had a supercomputer like the one that I am showing you here on the right side, that is one of our supercomputers at the Supercomputer Center in Jülich. And if you used a supercomputer, which is for the general audience, just group of computing infrastructure that has been optimized to work together and solve larger computational problems, and also to deal with large amounts of data, then you could see that use cases like this could be addressed in the manner of hours or days instead of months or years. So just to give you a quick example, coming from exactly this use case, if we had a virtual big brain model with these 270,000 brain nodes that Marmaduke mentioned at the beginning, if you had a normal workstation with a normal graphic processing unit, and you would like to process something like 50 subjects under this configuration, so 50 individuals, it would take you about 4.5 years to do that. However, on a supercomputer where you could launch many simulations at the same time, and using the memory efficiency, the communications efficiency, and the computing efficiency of the supercomputer, you could probably finish this in about 4 weeks. And I'm not going to touch the point that even with non-optimized code, on a normal laptop, on a normal CPU, this would take about 300,000 days. So we just don't go there because it's just probably unfeasible. But in order to address this, it comes the question, well, not everybody has access to a supercomputer, right? So we don't have one. You cannot go to the corner store and just buy one. And so to address this, the Phoenix infrastructure is being built. So the Phoenix infrastructure is built by 6 supercomputing centers in Europe who want to provide computing resources for research. And there, the IC project is in charge of providing neuroscience a gateway to these resources that are becoming available. They're creating this infrastructure. And they work in tight collaboration with EBRAINS in the sense that EBRAINS provides platform services in order to make easy access to the infrastructure and computing power. So this is really, really important because it provides then all access to the really computational power that is required to address these new scientific questions. For example, we have here the workflow that we have discussed during the webinar. So from the atlas to the model definition to simulation and then to scientific validation and all over. And all these are supported by EBRAINS platform services, from the EBRAINS Atlas services to the collaboratory where you can do the model definition and data integration, to all the interfaces to go to the computing infrastructure and so on. But of course, EBRAINS is not only about going fast and solve everything quickly, but do it good. And so we provide around all the hardware infrastructure and all the platform services, tools to do correctness analysis, usability enhancements, reproducibility, which is really, really important in neuroscience, quality assurance of the code that you're using, and monitoring the resources that you have available. So in a nutshell, what EBRAINS and Phoenix come together to provide a computing infrastructure which is exactly designed to address these very highly demanding computing scientific use cases, and provides all the interfaces to put together different components and then also come up with new scientific questions afterwards. Mm-hmm.
Yeah.
Yeah,
I love you all ended. Yeah, I love that ending. You went, and I went, yes, and I do, and I'm listening. That's so clear. Thank you so much, Sandra. So very clear. I'm not going to ask Victor back for the moment because I'm going to ask the 3 gentlemen back, and we're going to go through a myriad of questions that have come in. I have 2 for you just to complete. And if I miss anything out, you can add it. But what makes it possible for this particular workflow to benefit from such a large computing infrastructure?
Yes, it is not only about having access to the hardware. You need to actually have the right software and the right interfaces to access the hardware and make use of it. it doesn't make sense if you run a non-optimized code on a very large supercomputer, because it will take exactly the same time as if you did it on your laptop. So the important thing here is the whole effort put around making optimized code using a very mature software infrastructure like DBB, together with a very mature elements for interaction and grabbing data as the brain atlas. So these components make it possible.
Thank you. And a question about accessibility. You were talking about it's providing neuroscience with a gateway there when you were talking about Phoenix. So can anyone access those computing resources?
Yes, so actually every researcher in Europe can request resources from Phoenix through the IC project, and international researchers, through collaborations with European researchers, can also have access to these resources. So I would encourage everybody who is interested in getting access to these resources. I'm sorry, I didn't put the website here, but you can just look for phoenix-ri.eu, and there's all the information about how to access and what are the different ways to get access to the resources to power your research question, and also make use of the virtual big brain when everything comes available.
Thank you. And don't worry if you didn't catch that. I love the spelling out there. Ladies and gentlemen, you know that you can just contact the project for anything to do, well, with anything to do with the project, but for anything to do with today's webinar. So can I invite our gentleman back? We have 10 minutes. And after those 10 minutes, I hand over to Victor for a couple of takeaways. So ladies and gentlemen of the audience and my lovely speakers, we will close at 1:05 today. We're just going to take a few more minutes. So what have we had coming in? I'm going to go straight into questions. Here we go. I assume the virtual big brain is taking a snapshot of an individual's brain, but how do we account for long-term changes due to plasticity? Is this considered in the models used?
Mm-hmm. Maybe.
Yeah.
I can say a bit to this.
Yes, please do.
Plasticity. So yes, we are taking a snapshot of the individual's brain. On the one hand side, plasticity is essentially very slow changes. Yeah? And there are different forms of plasticity that can be considered. And this is a very active research area that these long-term changes, that they are being integrated into, in particular, the brain region model. So at the moment, it's not in there, yeah? But we and other groups are working on it. With regard to going beyond snapshots, there are huge efforts in place, for instance, to work on aging cohorts. Yeah, and this is a beautiful example. Oh, so over age, where we're looking at group data, and there we have structural changes as the brain ages. And these are aspects that we can actually address because they're expressed in the structural changes. This is not directly plasticity, but we are using the evolution or a trajectory over age to follow these changes. And this you cannot do with experimental data. The longitudinal studies is extremely difficult to do on an individual basis. This is a beautiful example where the virtual big brain modeling we have in EBRAINS can become actually very, very helpful. Individual aging trajectories.
Thank you. I like the word beautiful. You can put that anything to do with this project. I would like you to use the word a beautiful example. I love that. Right, let's see what else is there, because I think we've got quite a lot. Remember, lady and gentlemen, can you please keep things delightfully concise? Well, there we go. I'd like to ask how I learn about using this, because so who would like to come in here?
Maybe I can
please do.
say a little bit. So, the Human Brain Project actually provides many possibilities for learning how to use the brain simulation platforms and infrastructure. You can go to the education website on the HBP, and you will find tutorials and many other information about this. But you can also navigate in the eBRAINS.eu website to go to the virtual brain if you are more interested on that. And there is a specific section that will tell you more about tutorials and information on online courses for this tool as well.
Thank you, Sandra. And you are the best person for providing links. Just let everybody know that hopefully we'll be able to, I love it, we'll be able to post those links underneath at the end. So, and if not, as I said, you can, of course, get in touch with the project. Regarding representation, gender and ethnicity taken into consideration, or is it just a European male brain in the data? So tell us, talk to us, Timo Marmaduke, about that. Who wants to?
I can probably
please.
give an answer to that.
Thank you.
Of course, we try to provide as much coverage of the variability as is possible, and on the scale of neuroimaging, most of the data we have is, of course, reflects a much larger variability than this. On the postmortem scale, this is, of course, difficult, and the big brain that I've just shown is, of course, a single subject with a single gender. But as I showed in my presentation, we are providing access to samples from postmortem data that are typically taken from different subjects, and there's typically also some measurement of the variability. For example, the receptor distributions that I've shown are typically sampled in multiple subjects, different tissues, and we show the variation in those. Yeah. But of course, there is a problem in acquiring postmortem tissue. You don't have a free choice of all the ethnics and genders and so on. It's not so easy to. You cannot sample as you like from the population, of course.
Okay, and don't forget, ladies and gentlemen, we're just giving a quick answer on these. Can I say, I know that you are busy people, but if our audience might be frustrated because we cannot get to everything, I know they can go through the project and get in touch with you as long as you are not overwhelmed. Would that be a fair thing to say to our audience if we don't get to everything? Timo Marmaduke, does that sound reasonable? Okay, all right, thank you. And Victor, so here we go. How do you use participant data to contribute to the functional mapping? Is the functional mapping on average all the participants in your database?
Marmaduke or me?
Yeah.
I can start maybe. So we are putting emphasis on understanding inter-subject variability, because as you asked, Katrina, in the beginning, does the individuality of the brain matter? And the answer is yes. Mm-hmm. So we are focusing on the personalization of the brain models in the context of virtual big brain. And that's the reason why an average would not make any sense. So average sometimes we use in order with particular metrics, where we collapse everything in a meaningful metrics in order to guide us through these very high dimensional parameter spaces. But afterwards, we need to take into account the inter-subject variability. That is a very important factor, because the brain is a highly complex system, nonlinear, dynamic. You cannot average, in particular, we're talking functional data. So these are the functional brain imaging data. You cannot simply average it. You can take it as a first step, but then afterwards you have to be respectful to the individuality.
Yeah, I wanted to add, Marmaduke.
I would just add that the algorithms, the code that we're writing is built from the ground up to accommodate a cohort of subjects, and we don't, even when the computation is a bit intense, we always plan on doing these simulations on a per subject or per patient basis, and the tuning therein is also on a per subject basis. So there's no averaging on the simulation side.
Okay, and sorry, ladies and gentlemen, if you heard my scribbling on my garden table that's in my office here, so because I'm not on mute, but for the ease of speed, I'm keeping my mic on. Is it possible for non-European researchers to request access to the server as well?
Yeah, so this depends. I will answer this. This depends a lot on the specific case. It also depends a lot on if you already have collaborations with European researchers. So I would encourage everybody who has, who would like to get access, just to go to the website that will be put at the end of the webinar somehow underneath the screen, and contact the IC project coordinators to get to see if you can get access.
And I think that's a very good place to just stop for a moment, and just at 12:59 to take a regroup. Do we need to add anything on, you know, how to learn to use it, when and where, access to the EBRAINS atlases, whether they're openly accessible? Is there anything that I didn't give you a chance? Because it's important with this audience. Yeah, Victor.
Very, very quickly, because learning and education was an important aspect. We'll be also looking in neuroethics. So just to make you aware of this, we don't have time to speak about this, but be aware of it. But at the moment, we are developing what we call competence centers and facility hubs in EBRAINS. So these will be centers all over Europe where we are trying to centralize either competencies or facilities and allow researchers to come in and interact directly with EBRAINS experts, and learn about how to use the brain simulation, the models, etc. This is in development. Please keep your eyes open for these competence centers and facility hubs.
Okay. Thank you. Before I ask you for a couple of last words, have you said all the important stuff here? And we are providing links. Sandra, Timo, Marmaduke, anything that you didn't get the chance to say?
One thing that we should emphasize again, I think it has been said, but of course EBRAINS has support teams and has support contact on the website. So if anything is unclear, anything we said, you could always go to ebrains.eu, find the support page, and you will be forwarded to all the other resources. I think that is important to emphasize.
Thank you. So I'm going to ask in a moment for a couple of last takeaways or emphasizers from Victor. I think it's very interesting. I think when we spoke before this, Victor, you did talk about it helps with brain health trajectories. So it can help policymakers, because there are ways in which this can help you to intervene earlier. You can see brain activity in a much more precise location, the benefits of not having to remove a chunk, but just pathological tissue, all of those different things that I think you didn't get a chance to articulate, but it was a good link, I think, to policymakers that I just wanted to emphasize there in the practical applications thereof. But what else would you like to just underline before I gently close this webinar?
With regard to, I think what I just liked in the last 10 minutes in particular is the openness of EBRAINS, that when you're just beyond virtual big brain, but the community is invited to contribute. We will do our best to teach, to interact, to open up and adapt to the needs of the community, because this is a European digital neuroinformatics platform that we as a community want to build. So I would invite the community to contribute and to interact and to help us build EBRAINS. Yeah, this is, but in the last 10 minutes, it came out with the contributions from Sandra, Timo, Marmaduke. So I'm personally very excited about this. I want to make this very clear. Yeah.
And your excitement is absolutely infectious. All of you have been incredibly passionate, but let me tell you, I think you've seen that. I think the audience's excitement has almost been, if we were in the same place, we're not palpable. There you have the link, which is fantastic. Thank you. And that leads me to thank very much, ladies and gentlemen, the fabulous team behind the scenes, the technical team, the communications team, who are also responsible for keeping the lights on and everything, well, the show on the road. So let me be clear about that. Of course, I thank you, my delightful speakers, for synthesizing the contents of your incredible brains into such a short space of time and such short presentations, but a fabulous discussion. Let me tell the audience that, of course, if you enjoyed it, do tune into the next one. You just need to keep your eyes on the website, and we'll let you know when the next in the series is coming along. There's always something fabulously stimulating, which we unpack for you in the most accessible way. And of course, you can still share Brain Matters, #Brain Matters @Human Brain Proj. So that remains for me and for all of you. We can give these lovely regal waves to our audience and thank them very, very much for joining us at this lunchtime on a Friday. I wish all of you a very, very good afternoon and weekend, and I bid the audience a lovely warm farewell too. Thank you from me, Katrina Sickle.